Hello and welcome to this revision session for AQA A-Level Physics Paper 3 on the option of Astrophysics and on the topic of telescopes. So in today's revision session we're going to look at how to answer examination questions for A-Level Physics Paper 3, in particular the Astrophysics section. So in this, if we're successful and we've learned in today's revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you be preparing for this revision session? When you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this left hand side section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure to write in full sentences and show your full working out. Whilst in the right hand side section, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for your A-Level Physics? So the first step in revising independently for your A-Level Physics is to learn the key facts. Use revision guides, class workbooks, student prep notes and the textbooks to learn the key ideas of the course. You may wish to make mind maps or write out notes yourself. The second step is to retrieve your knowledge and understanding. So after this, what you should be doing is you should be testing yourself. So using things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you may wish to do some cue cards. Now the third step is to practice examination style questions. So use exam prep books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work, and you may wish to download your own examination past papers to do this. So our three steps of learn the key facts, testing yourself and practicing exam style questions are how you should be revising for this particular examination. Now in this revision session we'll be looking at three types of questions. The first type of question is your general check question, the basic questions designed to probe your understanding of the key concepts of the topic. The second type of question is a checkpoint question. So these are more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. Whilst the third type of question is an assessment point question. So these are past paper examination questions which will mimic the type of questions found in public examinations. So let's now start our revision on telescopes. So the first question says a magnifying glass has a focal length of 15 centimeters. It is held 5 centimeters away from a component which is being examined. Determine the magnification of the images. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to remember that if it's got a focal length of 15 centimeters, we can say f is 15 centimeters. It's held 5 centimeters away from the components being examined, so u is 5 centimeters. We've then got to use our equations for lenses, which is 1 over f equals 1 over u plus 1 over v. Pop in all the values, and you get v to be minus 7.5 centimeters. Now we also know magnification is going to be v, which is the image length divided by u, the object length. So it's 7.5 over 5, so it's the magnification of 1.5. The next question say the James Lick telescope at the Lick Observatory in California, USA was built in 1888 and is still in use. It has a primary convex lens of 36 inches and a focal length of 57.8 feet. What is its magnification if used with the eyepiece of focal length 55 millimeters? What is the sum of the focal lengths FO and FE, and how would you calculate change for an eyepiece of focal length 35 millimeters? Calculate the angular magnification of a telescope with an objective lens of focal length 1200 millimeters using an eyepiece of focal length 25mm and 10mm. Then the moon has an angular size of 0.5 degrees in the sky when viewed with the naked eye. Suppose the moon is viewed through a telescope with an objective focal length of 100 centimeters and an eyepiece of focal length 200mm. What is the angular size of the moon as seen through this telescope? And the 1 meter diameter objective lens of the Yerke refractor weighs 225 kilograms. Suggest two factors that limit the size of refractors for astronomy. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know in the first case, FE is going to be 55 millimeters. So magnification we know is FO over FE. That's an equation you've got to learn. Pop in all the values, so our magnification is 320. Now we also know that FO plus FE is going to be 17.6 meters, which should be the entire length of that telescope. Now again for the second one, FE is 35 millimeters. Pop in the values for magnification, and therefore we get 503. And again, the total of the two added up again is about 17.6 meters. Now in this next one, like we said before, magnification is going to be the objective focal length divided by the eyepiece focal length. So it's 1200 as given divided by 25. You don't need to convert millimeters into meters because it's a ratio, so we get 48, whilst for the second one it's 120. Now we also know here that we can work out the angular size, because we can say magnification is going to be the angular size of A over the angular size of B. So in this case, you know, the moon has an angular size of 0.5. We've got our objective focal length and our eyepiece focal length, so we can equate them and say angular size of A over the angular size of B is equal to FO over FE. You pop in all the values, you work it through, and it's 25 degrees. Now in the next question here, okay, what's the two factors here? Well, one factor is that refractors with a high magnification will have large objective lenses, which makes them very long. So we need to have giant domes to house them. And another factor is that you've got to make large glass lenses that are so heavy that the gravity causes them to sag under their own weight, because you can't support it in the middle because it will block out the light refracting through. So therefore it distorts their shape, and therefore the image that is formed will also be distorted. The next question say, a telescope is used to observe distant galaxies. It has an FO of 0.52 meters and an FE of 0.0010 meters. Calculate the magnification of the telescope. The image of a distant galaxy by a telescope subtends an angle of 0.331 radians at the eye. Calculate the angle subtended by the galaxy at the unaided eye. Then what assumptions can be made about light rays reaching the Earth from a distant object in space? What type of image is formed through an eyepiece lens of an astronomical telescope, and then give an equation for the magnification of an astronomical refracting telescope in terms of the focal lengths of the lenses, and then finally explain why astronomical refracting telescopes have to be very long to produce a highly magnified image. So pause the video now, then unpause the video when you want to go through your answer. So in this first question, how to work out the answer? Well, the magnification, as we talked about before, is going to be FO over FE. So you're keeping the same units to get the ratio out to be 520, the magnification. Now again, our other way to work out angular magnification is the angle of the angle subtended by the image divided by the angle subtended of the object. Rearrange it to get into the angle subtended by the object. Pop in all the values through. Remember, the magnification of the telescope will be constant in this instance if the lengths don't change. So therefore, it's 6.365 times 10 to the minus 4 radians. Now our assumption about light rays reaching the Earth from a distant object in space is that they've travelled so long that the light rays are now parallel to each other. Now you should know this is a fact. The image formed through an eyepiece lens of an astronomical refracting telescope should be a magnified, upright and virtual image formed in the eyepiece lens. Now again, the equation that allows you to find the magnification for an astronomical refracting telescope is FO over FE, and we know that because that's the equation for magnification, an astronomical telescope needs to have a large FO to get a large magnification. So if that focal length is very long, therefore the telescope will be very long. The next question says, what are the advantages and disadvantages of a refracting telescope? So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, the advantages are that refractors require less maintenance than reflectors, and refractors are also not as sensitive to temperature changes as reflectors can be. But the disadvantages of a refractor tend to be 5 key issues. It's the size. Firstly, it's difficult to make large diameter glass lenses which are completely free from defects when you need them to refract. Now, a larger magnification requires larger objective lenses, so therefore very long focal lengths. Your telescopes are very, very long in construction. The second issue is the weight. So large diameter lenses are very heavy and tend to distort under their own weight, especially because we can't support them behind them. So therefore the refractors are also very heavy and then difficult to move into position, so can't respond to astronomical events as quickly. In terms of construction, the lenses can only be mounted and supported around their edges, as we mentioned before, but that's actually where they're the thinnest and the weakest, so that is also an issue. The image quality will suffer because refractors will have both issues with both chromatic aberration and spherical aberration, and again the ability to observe non-visible wavelengths is difficult because refractors will only be able to observe wavelengths of visible light. Now the next question says, what are the advantages and disadvantages of reflecting telescopes? So pause the video now, then unpause the video when you want to go through your answer. Right, in this next question, we can link it through to the different parts of the reflecting telescope. So the advantages are, firstly, that their size. The diameter of a mirror can be much larger than that of a lens, so the greater magnifications can be achieved. The arrangement of the mirrors will also allow reflectors to be much shorter in length than refractors, because several small mirrors can be used to form one large composite mirror. Secondly, the weight. Now, the large single mirrors can be made which are more light and easily supportable from behind, because you don't need to worry about blocking out light passing through the mirror. So reflectors tend to be lighter, which allows for more rapid responses for astronomical events. In terms of constructions, mirrors only use the front surface for reflection, which eliminates many of the issues that you get when you've got a lens which has has two surfaces, but also goes through the particular glass as well. So therefore it means the mirror surface can be made very thin, which allows for a greater image detail. Now, mirrors cannot produce chromatic aberration, but they will suffer from spherical aberration, but only if non-parabolic mirrors are used. And again, reflectors can be designed to observe wavelengths of light from outside the visible spectrum, so reflectors can be sent into space, which also eliminates light absorption due to the atmosphere. Now, the disadvantages of a reflector are that the secondary mirror will block out some of the light from entering the primary mirror, so you'll lose some of the information from your source. The secondary mirror and its support will also cause some diffraction as the waves pass along the secondary mirror, which will affect the clarity of the image. The mirrors in reflecting telescopes are also exposed to the air, so will require regular maintenance, and that'll cost more money. And then finally, light is refracted in the eyepiece lens, so you will get some chromatic aberration at the stage of refracting it into an image to be observed by a human. The next question says, a reflecting telescope with a parabolic mirror has a diameter of 80 centimeters and a focal length of 1 meter. It is used with an eyepiece of 15 millimeters. What is the magnification of the telescope? Then what is the magnification of a Cassegrain reflecting telescope whose mirror has a focal length of 2,800 millimeters and is used with eyepieces of focal length 5 millimeters, 15 millimeters and 25 millimeters? So pause the video now, then unpause the video when you want to go through your answer. So for this first question, how can you work out the magnification? Well, as we said before, magnification is FO over FE, so we've got to keep it in the same unit, so it's 1 over 15 times 10 to the minus 3, so it's 67. In this next one, we're doing the same unit, so we're fine, so it's 2,800 over 5, 560. Next one, 2,800 over 15, 187. And then finally, 2,800 over 25, which is 112. The next question says, what is the resolving power of a telescope? What sort of pattern is produced when light passes through a circular aperture? What is the central part of this pattern called? What effect does this have on the resolution of the telescope? What is the Rayleigh criterion? Give 3 examples of problems when using refracting telescopes, and give 2 advantages of using reflecting telescopes compared to refracting telescopes, assuming they have the same magnification and the resolution power. So pause the video now, then unpause the video when you want to go through your answer. Right, the definition of resolving power, you've got to learn it, is how much detail a telescope can see. Now, when you pass through a circular aperture, the light will diffract and produce a diffracting pattern. Now, the central circle of this pattern, which will be a circular shape, is called the airy disk. Now, a telescope is defined to have a poor resolution if the airy disk of light that makes up the image overlaps with that first maxima of your image being produced. So the Rayleigh criterion in an equation is theta is equal to lambda over d. Now, the issues with refracting telescopes are you'll get chromatic aberration, bubbles and impurities in the lens which will absorb or scatter radiation, so you won't get a very clear image. Building lenses of good quality is expensive and difficult. Large lenses are heavy and can sag, and for a large magnification a refracting telescope needs to be very long and it can be difficult to house. Now, the advantages of reflecting telescopes are it's easier to make good quality mirrors. Mirrors do not suffer from chromatic aberration. It's cheaper to make larger mirrors than lenses. Lenses can be supported from underneath, so are less likely to sag as well. The next question says, the supermassive black hole at the centre of the Milky Way galaxy is 25,000 light years from the Earth. It has a Schwarzschild radius of 1.2 times 10 to the 10 meters and emits radio waves at a frequency of 230 gigahertz. The Event Horizon Telescope is an array of radio telescopes which has the same resolution as a single radio telescope with a diameter of 8,000 kilometers. Calculate the minimum angular separation, which could be resolved by the EHT, then deduce whether the resolution of the EHT is suitable to obtain a detailed view of the supermassive black hole. Support your answer with a calculation. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what can we say? So, the minimum angular separation is going to be linked to the wavelength. So we can say lambda is equal to c over f. So you can pop that all through. Remember, f is going to be linked into what you've got here. So you've got 230 times 10 to the 9 there. So you can work that all through. So you get, and then when you work out your wavelength, you can then link that into your angles by then turning it into that by times by 8,000 times 10 to the 3. So therefore you would get 1.63 times 10 to the minus 10 radians. So this means that the EHT can obtain a detailed view of objects down to the angular size of 1.63 times 10 to the minus 10 radians. So that will then allow you to work out your minimum angular resolution. We also know that theta is equal to s over d. That's an equation which you've covered before in mathematics. So you can say theta, the angle, is equal to s, the distance, over d, as so. So you can pop in all your values, you work it through, and you get 1.01 times 10 to the minus 10 radians. So we can see here that the value of the minimum angular separation divided by the telescope is greater than the angle subtended by the actual supermassive black hole. So that's about 1.6 times greater than the limit, so therefore it wouldn't be able to resolve a detailed image of the black hole. So the angle of the black hole can be, as viewed from the Earth, is wider than the angle that the telescope can view. The next question says, the largest refracting telescope still in operations is the Yerkes refractor. The construction of this telescope later paved the way for the Otto Struve reflector to be built. Both telescopes detect optical wavelengths of light. So the table below summarizes some of the properties of the two optical telescopes. Now compare the two telescopes in terms of their collecting power and resolving power. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, collecting power, we should be able to understand that collecting power is proportional to the area, which is proportional to the diameter of the telescope squared. So you can see that the ratio of the two collecting powers is going to be the ratio of the two diameters of the telescope squared. So you do 208 over 102, square it, so you get about 4. So that tells you that the Otto Struve reflector is about 4 times greater than the Yerkes refractor, meaning it'll produce brighter images. Now for our resolving power, or the minimum angular resolution, is proportional to 1 over d, because theta equals lambda over d, the Rayleigh criterion. Now you don't need to consider lambda here, the wavelength, because we'll just say it's the same wavelength for both. So you can do the ratio of the two of them. So you do 102 over 208, so it's 0.5. So that tells you that the Yerkes refractor can resolve detail half as well as the Otto Struve reflector. So it means that the resolving power of the Otto Struve reflector is twice as great as the Yerkes refractor. So not only will it produce brighter images, it'll also produce clearer images as well. It's very important to link those conclusions into your answer. The next question says, compare and contrast a radio telescope with an optical telescope. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what do we know? That for an optical telescope, they're similar because they both use parabolic surfaces to reflect waves, but the differences are a radio uses a single primary reflector whilst the optical uses 2 different mirrors, and a radio dish does not need to be as smooth as an optical mirror. In terms of positioning, both are ground-based as the atmosphere is transparent to both radio and visible light waves, but the differences are that the optical has to be placed higher up to avoid atmospheric distortions and also away from cities to avoid light pollutions, whilst our radio telescopes must be located remotely away from populations, so will be away from radio sources. Now both of the telescopes are used to detect hydrogen emission lines, but radio waves are not absorbed by dust, but optical waves are, so therefore radio telescopes are used to map the Milky Way where there's lots of dust. Now, in terms of linking this through, we can say that for resolving power, radio waves are longer than optical waves, so the radio telescopes have a much lower resolving power than optical telescopes, and optical telescopes are more likely to produce detailed images. Now, in terms of collecting powers, radio telescopes are larger in diameter, so have a greater collecting power than optical telescopes, so therefore it's more likely that radio telescopes will produce brighter images, but many radio sources in the night sky are very weak. The next question says, compare and contrast an infrared telescope with an optical telescope. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this one, what's looking like for our optical and our infrared? So in terms of similarities, both infrared and optical are use primary concave mirrors and a secondary convex mirror. The differences are, though, the mirrors in an infrared telescope must be kept very cool to avoid interference from the telescope itself producing infrared radiation. In terms of positioning, many ground-based telescopes can detect both optical and near infrared as long as they're positioned away from cities and are high above the ground. That's because infrared radiation is strongly absorbed by water vapor in the atmosphere, so telescopes must be built in a very dry, high altitude location such as a desert or above the atmosphere in the mountains. Now, the atmosphere is transparent to most optical wavelengths but does block a lot of infrared wavelengths, so space-based infrared telescopes are preferable to Earth-based ones. And in terms of uses, most objects emit visible light and infrared radiation, so you can get information on an object from both these types of telescopes. Now, infrared telescopes can detect warm objects that don't emit visible light, such as dust in nebulae which has been heated up, or also brown dwarfs. Now, in terms of the resolving power and the collecting power, infrared telescopes have a lower resolving power than optical telescopes of the same size because from the Rayleigh criterion they have a longer wavelength. But the collecting power of infrared and optical telescopes will be similar because their diameters of their dishes are similar in size. Now, the next question says, compare and contrast an ultraviolet telescope with an optical telescope. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, what's our similarities? Well, in terms of structures, both UV and optical telescopes have a primary concave mirror and a secondary convex mirror. In terms of differences, mirrors in the UV must be much smoother than those of optical telescopes because of the wavelength of UV. In terms of positioning, many space-based telescopes can detect both optical and UV wavelengths. Now, all UV wavelengths are strongly absorbed by the atmosphere in the ozone layer, so UV telescopes must be located in the upper atmosphere or in space. So therefore, space-based UV telescopes can be inconvenient to maintain and are a lot more expensive. Now, in terms of uses, both can be used to detect the chemical compositions and temperatures of objects. And many objects that emit visible light will also emit ultraviolet radiation, so you can get information on the object from both telescopes. Now, UV telescopes can detect objects not visible at other wavelengths, such as very hot gas clouds near stars, supernovae explosions, and quasars. In terms of comparisons for resolving power and collecting power, UV telescopes have a much higher resolving power than optical telescopes of the same size because of the Rayleigh criterion. They have a shorter wavelength. In terms of collecting power, again, they're very similar to each other because the diameter of their dishes are very similar. The next question says, compare and contrast a gamma ray or X-ray telescope with an optical telescope. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what can we say? Well, the structure of X-rays and optical telescopes are similar because they both use parabolic mirrors to reflect and focus waves. Now, X-ray telescopes are made from a combination of parabolic and hyperbolic mirrors, which are going to be very smooth because of the low wavelength of an X-ray or gamma ray. And gamma ray telescopes don't use mirrors at all, but they'll use specialized detectors and grazing mirrors to ensure that the telescope works. In terms of position, an X-ray, gamma ray and optical will all perform best when positioned in space or away from anything to do with the Earth's atmosphere. Because all X-rays and gamma ray wavelengths are strongly absorbed by the atmosphere, so again they should be located in space. But again, these types of telescopes are difficult to maintain and to repair. In terms of uses, X-rays and gamma rays can provide additional information about visible objects such as supernova remnants, and X-rays and gamma rays can observe non-visible objects in very energetic events such as neutron stars, black holes, pulsars and gamma ray bursts. Now, when we compare the resolving power of the telescopes, the X-ray and gamma rays will have a much higher resolving power than the optical telescope because they've got a much shorter wavelength, linking it into the Rayleigh criterion for the same diameter dish. Now, in terms of the collecting powers, the X-ray and gamma ray telescopes have a much lower collecting power because they've got much smaller dishes that they use them for. However, X-ray and gamma ray sources tend to be extremely bright, so it can compensate for that. Now the next question says, give one advantage and one disadvantage that radio telescopes have compared with optical telescopes. Then explain why most infrared observations have to be carried out above the atmosphere and what is meant by infrared windows. Then Sophia is a fly and IR observatory housed in an aircraft with a telescope objective dish of diameter 2.4 meters. If it is observing an object at a wavelength of 24 micrometers, what is its minimum angular resolution, and how will this compare with that of an optical telescope with the same diameter observing at 510 nanometers? So pause the video now, then unpause the video when you want to go through your answer. So to answer this first question, you've got to think about the radio telescopes compared to the optical telescopes in structure and when they operate. So the advantage of radio telescopes is it can operate day and night, while optical telescopes can only operate at night with clear skies and no visible radiation coming from the sun. The disadvantages though is that they operate at longer wavelengths because radio waves are longer, so therefore they'll have a poorer angular resolution than optical telescopes from the Rayleigh criterion. Now most infrared observations are carried above the atmosphere because the infrared ray wavelengths are absorbed by the water vapour in the Earth's atmosphere. Now infrared windows are parts of the infrared spectrum that are actually transparent to the Earth's atmosphere and therefore can reach the ground and ground-based telescopes without being absorbed. Now we can work out the minimum angular resolution by making sure we're using the same wavelength, so convert our nanometers into meters and our micrometers into meters, pop them in there, and you can work it through to be 1 times 10 to the minus 5 and 2 times 10 to the minus 7 meters. Now that therefore tells you that the optical telescope has an angular resolution of about 100 times better than the infrared telescope of the same diameter, mostly because of the wavelength of the light itself. Now the next question says the IUE has a parabolic mirror of diameter 45 centimeters and focused UV radiation. For a wavelength of 120 nanometers, compare its minimum angular resolution and its collecting power with that of an optical telescope of the same diameter operating at 510 nanometers. Now the detector on a UV telescope uses a photoelectric effect to convert UV photons to electrons. Calculate the energy of a UV photon with a wavelength of 120 nanometers and explain why it's necessary for most IR and all UV and X-ray telescopes to be positioned in space. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, once again, we work out a minimum angular resolution by using the Rayleigh criterion. So theta equals lambda over d. Pop it in there, and you get the IUE to be 2.7 times 10 to the minus 7 meters, and the optical telescope to be 1.1 times 10 to the minus 6 meters. Remember to keep our wavelength and our diameter into meters. So therefore, the resolving power of the optical telescope is about 10 times better than that of the IUE. Their collecting powers are the same though, because if you notice from the information, they've got the same objective mirror diameter, the only factor that affects the collecting power. Now the energy of the UV photon is E equals hc over lambda, an equation from paper 1. Pop in all the values, convert your nanometers into meters, work it all through, and we get 1.66 times 10 to the minus 18 joules. Now infrared, UV and X-rays are heavily absorbed by the atmosphere of the Earth, so such telescopes need to be positioned in space above the atmosphere where these wavelengths are not blocked. The next question says, compare and contrast a CCD with a human eye in terms of a detector. So pause the video now, then unpause the video when you want to go through your answer. Right, so what's a comparison? For a human eye, the quantum efficiency, the number of photons in every 100 that will be detected by the detector, is about 1% for a human eye, but for a CCD is very high, 70% or above. So you're much more able to detect fainter objects. In terms of the resolution, the human eye is about 100 micrometers, but the CCD is about 10 micrometers, so you can see in much more detail with a higher resolution, and this could be increased even further by using smaller pixels. But for convenience of use for the human eye, you just look, so it's very easy. But for a CCD, you'll need remote viewing. The images can be stored and analysed digitally and sent across the internet, but you can have longer exposure times than that of the eye because you can alter it, and the CCD will also detect a wider range of wavelengths than the human eye will, which will only detect visible radiation. The next question says, a student investigated how the nature of the image depends on the position of the object in front of a large converging lens. The diagram shows one position for the object. Complete a ray diagram to show how the image of the object is formed, then describe the nature of this image relative to the object. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you can do here is you can see in this first response here the diagram that you would have to draw. So you'll get a mark for going through the center of the lens directly, and then the second one parallel to the axis. Then when it reaches the lens, it'll go through F on the right hand side, or you could go through F on the left hand side, and then when it reaches the lens, it goes parallel to the axis. Now the image that you would form, as you can see on the screen, is going to be inverted. It's the wrong way around. It's magnified because the line is longer, and it's real because the lines actually cross. The next question says, explain with the help of a diagram what is meant by a refracting telescope being a normal adjustment. Your diagram should include the paths of two rays and show the position of the focus of the object and the eyepiece. Then a refracting telescope used by an amateur astronomer is a normal adjustment when looking at the moon. The telescope is 1 meter long and has a maximum useful magnification of 200. State the focal lengths of the objective lens and the eyepiece lens. Then a spacecraft is in orbit around the moon at an altitude of 50 kilometers. It is trying to find the landing site for one of the Apollo moon missions of the 1970s. The descent stage of the Apollo lunar module that was left on the moon is 4.3 meters wide. The orbiting spacecraft is equipped with a telescope with an angular magnification of 200. What is the angle subtended by the image of the Apollo descent stage by the spacecraft above the moon's surface? Then explain what is meant by chromatic aberration and how it is corrected in a convex lens. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can see the diagram showing normal adjustment. It's the idea when you have your objective lens and your eyepiece lens that where the lines cross for both the objective lens and the eyepiece lens, it's in the same position if they're in normal adjustment. We also know here that FO is equal to 1 minus FE, so you can then work it through, and we know FO is what it's going to be 1 over 200, so you can work it all through and you get 955 millimeters. For the eyepiece length, it's going to be the difference because you know the overall length is going to be 1000, so you know that the FO is equal to 995, so 995, so therefore the answer will be 5. Now in this next one, we've talked about this before, S is equal to R theta, so therefore theta is equal to S over R, so it's 14.3 over 50 times 10 to the 3. So you're looking at S, the length, and over R, the radius of the circle that you'll be producing for your angle. So therefore you work it through to be 2.7 times 10 to the minus 4 radians. Now chromatic aberration is due to the refractive index of the material being different for different wavelengths, so it'll be different colours. So the lens is unable to bring all visible wavelengths to the same point of focus. So this results in an image with fuzzy coloured edges, and so chromatic aberration can be reduced with the use of an achromatic doublet lens. So you would remove some of the different wavelengths. Okay, so it would be a composite lens of different types of glass that could bring two wavelengths like red and blue into focus at the same point. The next question says the diameter of the objective mirror of the Hale telescope is 5.1 meters and it's observing a star emitting a wavelength of 510 nanometers. What is the minimum angular resolution of the telescope in radians? What is the detail the telescope can detect on the surface of the moon? Planets have been detected around other stars. Estimate the diameter of a telescope objective lens required to resolve a Jupiter-sized planet orbiting the nearest star, which is about 4 times 10 to the 16 meters away, assuming you're observing at a wavelength of 550 nanometers. Then the Arecibo radio telescope has a dish diameter of 305 meters and has been used for observations using radio wavelengths as low as 4 centimeters. What is the theoretical angular resolution at this wavelength? How does this compare with the resolution of the Hale optical telescope? Then compare the collecting powers of the Lovell radio telescope at Jodrell Bank in Cheshire, UK, which has a diameter of 76.2 meters, the Arecibo radio telescope with a nominal diameter of 305 millimeters, and the Hale optical telescope, which has a mirror diameter of 5.1 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, angular resolution is lambda over d, the Rayleigh criterion. Make sure we're in the same units, and we get 1 times 10 to the minus 7 radians. So the smallest detail that you can see is therefore going to be this particular minimum angular resolution multiplied by the distance to it. So therefore it will be 38 meters. In this next one, we know at a distance of 4 times 10 to the 16 meters, the angular resolution of a Jupiter-sized planet is going to be lambda over d. So you work it all through, 3.8 times 10 to the minus 7 radians. So therefore the diameter of the lens needs to be approximately, from using theta equals lambda over d, 145. Now, the next one, the angular resolution, again, you work through to be 1.3 times 10 to the minus 4 radians. Now, the Hale telescope resolution is about 10 to the minus 7 radians from the previous questions. So that's about 1,000 times better. So despite the much larger sizes of the dishes, the angular resolution of the radio telescopes are a lot worse because radio wavelengths are a lot longer than optical ones, and theta equals lambda over d. And in the final one, remember what we've got to do, that the ratio of the collecting powers is the ratio of the squares of the objective diameters. So you would square all the different values, and you do each one like that to get 1 to 223 to 3500. The next question says, there's a supermassive black hole at the centre of the Milky Way galaxy. It is difficult to resolve images of the region around this black hole directly. Astronomers investigating the supermassive black hole detect radio waves at a frequency of 230 GHz. By correlating the information from several radio telescopes, they can obtain images with the same resolution as a single radio telescope with a diameter of 5,000 kilometers. So calculate the minimum angular separation which could be resolved by a radio telescope of diameter 5,000 kilometers detecting waves of frequency 230 GHz. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, how can we work it through? Well, we know the wavelength is going to be c over f, because with no c, it's going to be 3 times 10 to the 8, it's an electromagnetic wave. We've got f, it's 230 gigahertz, we turn that into hertz. So we get a wavelength of the radiation source. We can then say that the minimum angular resolution is the Rayleigh criterion. It's going to be theta equals lambda over d. We've just worked out lambda. We know d from the information is 5 times 10 to the 6 kilometers into meters. So we get 2.6 times 10 to the 10 radians. So 10 to the minus 10 radians, sorry. So the next question says, explain what is meant by the Rayleigh criterion. A telescope uses wavelengths in the range of 90 nanometers to 120 nanometers. Explain why this telescope must be located in space. Then table 1 shows information about 2 telescopes. Each telescope detects radio waves with a wavelength of 21 centimeters. Compare the performance of the telescopes in table 1 when both are used to observe the same faint radio objects. So pause the video now, then unpause the video when you want to go through your answer. So, to answer this first question, you've got to know the definition of the Rayleigh criterion. So it identifies the minimum subtended angle between two objects whose images can be resolved. So you've got to actually give more detail than this though, because it's the minimum angle when the central maximum of the diffraction pattern from one object coincides with the first minimum of the diffraction pattern of the second object. Learn that definition. It's very key and very crucial, not just the equation. Now, the advantage is that telescopes detecting UV or wavelengths smaller than visible light is very important because it indicates that it's going to be absorbed by the ozone layer, so therefore the atmosphere must be in the atmosphere is going to absorb it, so therefore the telescope must be in space. Now again, how do we link in our collecting powers? It is the square of the diameters, so we ratio the two, but we ratio the squares of the diameters, so it's 305 squared over 76 squared, so it's 16 times brighter. But just be careful about this because there's no absolute conclusion, because the image from the receiver will be brighter, but Lovey will likely have a better detail because of the type of dish shape it has. There'll be no spherical aberration, so you could argue either way about which one shows the best image. The next question says, the Arecibo telescope has a dish diameter of 305 meters and has been used for observations using radio wavelengths as long as 4 centimeters. What is the angular resolution at this wavelength? Then compare the collecting powers of the Lovell radio telescope, which has a diameter of 76.2 meters, the Arecibo radio telescope with a diameter of 305 meters, and the Hale optical telescope with a mirror diameter of 5.1 meters. Then give one advantage and one disadvantage that radio telescopes have compared with optical telescopes. Then Sophia is a flying IR observatory housed in an aircraft with a telescope objective dish of 2.4 diameter meters. So if this is observing an object at a wavelength of 24 micrometers, what is its minimum angular resolution? How would this compare with that of an optical telescope of the same diameter observing at 510 nanometers? And then why is it necessary for most IR and all UV and X-ray telescopes to be positioned in space? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, use the Rayleigh criterion, okay, and then you can work it through, and then you can actually get 1.3 times 10 to the minus 4 radians. Sorry, not the Rayleigh criterion, rather you would use the ratio, well, no, sorry, it is the Rayleigh criterion, it's the wavelength over the diameter. The next one, we can do the ratios of the collecting powers by doing the diameter squared, so you work that one through. The advantage is that radio telescopes can operate day and night, while optical telescopes can only operate in night with clear skies, but the disadvantage is because radio waves are at longer wavelengths, the telescopes will have a poorer angular resolution than the optical ones. The minimum angular resolution again is the Rayleigh criterion, so therefore you can link it all through, and you can note that the optical telescope has a much better angular resolution than the infrared telescope. And then infrared, UV and X-rays are heavily absorbed by the atmosphere of Earth, so such telescopes need to be positioned in space above the atmosphere where these wavelengths are not blocked. Now the next question says, draw a ray diagram to show how a convergent lens can cause spherical aberration. Then draw a labeled ray diagram for an astronomical refracting telescope in normal adjustment. Show the 3 non-axial rays passing through both lenses, and then label the principal foci of the lenses. Then the next question is, the James Lick telescope is an astronomical refracting telescope. When in normal adjustment, the distance between the lenses of the telescope is 17.4 meters and the angular magnification is 750. Calculate the focal length of the eyepiece lens. The James Lick telescope can be observed to identify binary stars. 2 techniques available using this telescope are using a processed image from a CCD and direct observation using the naked eye. Compare the use of the CCD with the use of the naked eye to observe binary stars with this telescope. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can see that in a ray diagram, you should have 2 pairs of rays drawn parallel to the principal axis, which are coming into different focus points or different foci. Now, the outer rays will focus closer to the lens than the inner rays, so you'll get different areas of focus, so you get different images forming, getting a blurred spherical image. The next question, you'd have both focal points labelled on the principal axis. FO is greater than FE. There'll be 3 off-axis rays through the objective lens correct as far as the eyepiece, and then 3 rays to the eyepiece correct with all parallel to the construction line as shown in the following diagram. Now in our next question, how can you work it through? Well, we know FO over FE is 750 because that's the angular magnification. We know the total length is FE plus FO, which is 17.4. We can then work that through and we get FE to be 2.317 times 10 to the minus 2 meters. Now in terms of comparing the two, the resolution is going to be limited by the diameter of the objective, so it'll make no difference, but the CCD does have a better resolution due to have smaller pixels, so the stars could be seen more easily as separate objects. The CCD will have a higher quantum efficiency and it can be exposed for a longer time, so therefore dimmer objects will be more likely to be observed, and it also can detect a wider range of wavelengths, so you can see more binary star pairs. The next question says, if the quantum efficiency of the human eye is about 4% and 10,000 photons fall onto a light-sensitive cell on the back of the retina, how many photons will the eye detect? Then summarise the main reasons why CCD is the detector of choice for modern astronomy. Then light intensity of 5.3 times 10 to the minus 3 watts per meter squared and a frequency of 3.9 times 10 to the 14 hertz fall on a pixel of area 4.2 times 10 to the minus 12 meter squared in a CCD detector in the focal plane of a telescope. The quantum efficiency of a CCD is 85%. How many photons of light are incident on the pixel per second, and how many of these photons are actually detected and produce a signal? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the detected photons is 4% of 10,000, which is 400. Now, CCDs have a higher quantum efficiency, so we can record fainter objects with shorter exposures. CCDs can store images electronically, you can send them over online for wider distribution. They can be processed as an image. They'll operate over a wider range of wavelengths than the eye, and they'll also have a linear response. And then finally, in this next question, power is going to be equal to the energy of the photon over time. So that's intensity times by area, so you can work it through to be 2.2 times 10 to the minus 14 watts. Now the energy of a photon is equal to HF, so you can say HF is going to be 6.6 times 10 to the minus 34 times by 3.9 times 10 to the 14, so you get 2.6 times 10 to the minus 19 joules. So in 1 second, that's 2.6 times 10 to the minus 19 watts, so the number of photons is therefore going to be 2.2 times 10 to the minus 14 over 2.6 times 10 to the minus 19, so that's in 1 second second, that's 8.4 times 10, 8.5 times 10 to the 4 photons. Now, because it's 85% efficient, so therefore 0.85 times this value is going to be 7.2 times 10 to the 10 to the 4 photons detected every second. The next question says, the diagram shows a convergent lens being used as a magnifying glass. On the diagram, use a ruler to draw two rays from the top of the object which show how and where the image is formed. Represent the image by an arrow drawn in the correct position, and then calculate the magnification produced by the lens. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can see the ray diagram that should be produced. So you can see here, you get the ray parallel to the axis from the top of the object, and it's refracted through the focus and tracked back through the object. Rays through the centre of the lens will go straight through and be traced beyond the object. Then the rays join the top of the object to the focus on the left of the lens to be taken to the lens refracted parallel to the axis and traced back beyond the object, and you can draw in your arrow as shown here. You will then look at the length of the different objects and do the image length over the object length, and you get your answer out to be 3. The next question says, draw a ray diagram to show how a convergent lens can be used to form a diminished image of a real object. Label the object, image and principal foci of the lens on your diagram. Then a student experimented with a convergent lens whose focal length was known to be approximately 50 centimeters. She placed an object and screen at a fixed distance of 200 centimeters apart. With the lens 128 centimeters from the object, she observed a sharp image on the screen. Calculate the focal length of the lens. Then the lens was used as one of the components of a simple refracting astronomical telescope. State whether the lens formed the eyepiece or objective, given reasons for your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you would draw a diagram as so. So you'd see that one line coming from the top of the object will go straight through the lens, being undeviated through the centre. And then one line will go through a parallel with the axis from the top, hit the lens and refract through F. Where the two lines cross, that is where the image is formed. We know from this information U is 128 centimeters, V is going to be equal to 200, the total length, minus 128 if you think about the distances between the image and the object and what U and V are, so that's 72 centimeters. We know 1 over F equals 1 over U plus 1 over V, the lens equation, so you can pop that all through and you get F out to be 46 centimeters. Now in this last one, okay, will it be an eyepiece or objective? Well, it'll be an objective lens, because you know M is equal to FO over FE, and so for it needs to be magnified, FO needs to be greater than FE to get a positive, like a value bigger than 1 for M. So as we know, the telescope length is FO plus FE, so therefore if the lens must be an objective one, because otherwise if that wasn't the case, the telescope would be very, very, very long, which we don't want it to be. The next question says, draw a ray diagram to show how a convergent lens forms a magnified real image of a real object. Label the principal focus on your diagram. Then draw a ray diagram to show how a convergent lens forms a magnified virtual image of a real object. Label the principal focus on your diagram. Then a convergent lens of focal length 145 millimeters is used to produce an image of an object placed 112 millimeters from the lens. Calculate the image distance with an answer to the appropriate number of significant figures, and then state 3 properties of this image. So pause the video now, then unpause the video when you want to go through your answer. So in this first question, you've got to draw your diagram in like so. Like we said before, one line from the top goes straight through the center and undeviated. One line goes parallel to the axis and then refracts through F. Where the lines cross, that is where you get your image. In this next one, you're going to have your straight line again parallel to the axis going through F, and again that line going from the top going straight through the center of the lens. Because they're diverging away, you trace them back to where they came from. Dash the lines because it wasn't actually from there, it's just a mistake of the human brain to think it's coming from behind that object. Where those two virtual lines cross, that is where you get your image formed. Now in this next one, we know that 1 over F equals 1 over U plus 1 over V. Pop in all the values and we get V to be equal minus 492 millimeters. Now you can use your diagram, but also the fact that V is a minus indicates it's going to be a virtual image, but from what you've seen before in the previous diagram, it's virtual, it's magnified and it's upright. Now the next question says, draw a ray diagram for an astronomical refracting telescope in normal adjustment. Your diagram should show the path of 3 non-axial rays passing through both lenses. Label the principal foci of the 2 lenses. Then the Treptow Giant Telescope in Berlin is one of the longest movable refracting telescopes on Earth. Some of the properties are summarized below. Then calculate the focal length of the eyepiece lens and the objective lens of the Treptow Giant Telescope, and then the images formed by the refracting telescope can suffer from chromatic aberration. Draw a labeled diagram to show how convergent lenses cause chromatic aberration. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can see the diagram is shown here. So you can see that the rays are off axis to get the mark. You can see that they've refracted through the objective lens there. They've met at the point where FO and FE there. They'll then hit against the eyepiece lens, and then they'll refract parallel to the construction line as drawn before. We know FO plus FE is 21. So FO over FE is 210 from the information given. So you can say 211 FE equals 21. So FE is 0.10 meters, so therefore FO must be 21 meters to get that final value out. Now again, how do we show chromatic aberration? It's that we're showing that when rays are going through that lens, that unfortunately that the red wavelength will refract at a longer wavelength, at a longer distance than the blue wavelength, which will refract shorter. So you get two different foci. The foci of the blue wavelength will be closer to the lens than the foci of the red wavelength. So you get those differences in focal points for the wavelengths. The next question says, draw a ray diagram for an astronomical refracting telescope in normal adjustment. Your diagram should show the path of 3 non-axial rays through both lenses. Label the principal foci of the two lenses. Then an early form of this telescope was built by Johannes Helvetius. It was 3.7 meters long and had an angular magnification of 50. Helvetius used it to produce one of the earliest maps of the moon's surface. Calculate the focal length of the objective lens and the eyepiece lens in an astronomical telescope of length 3.7 meters and an angular magnification of 50. Then the Triesnecker crater on the moon has a diameter of 23 kilometers. Calculate the angle subtended by the image of this crater when viewed through a telescope of angular magnification 50 on the Earth. Then early refracted telescopes suffered significantly from chromatic aberration. Draw a diagram to show how a single convergent lens produces chromatic aberration. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, as the diagram showed in the previous question, 3 parallel off-axis rays through the objective lens. The rays continue through to the eyepiece, emerging parallel to the construction line, and you label your foci where the two lines have crossed over, the FO and the FE. We know FO plus FE is 37, FO over FE is 50, so we can work out FO to be 3.6 meters, similar to the previous question, and FE is the previous equation, and FE is 0.074 meters. In this next one, we know that S equals R theta, so therefore theta is S over R, S being the diameter of the object and R being the distance to the object, put them both in meters, or you can keep them in kilometers to be fair, because there'll be a ratio, so it'll be 6 times 10 to the minus 5 radians. We know M is theta I over theta O, so we work that through to equal 3 times 10 to the 3 radians. And then the idea is with chromatic aberration that there'll be wavelengths, red wavelength will have the focus further away from the lens than the blue wavelength will as well. The next question says, draw a ray diagram for a Cassegrain telescope. Your diagram should show the paths of 2 rays up to the eyepiece lens. A spacecraft passes Pluto at a distance of 12,500 kilometers. The telescope on board has an aperture of diameter 0.21 meters and operates at a wavelength of 450 nanometers. Discuss whether this telescope is suitable for studying a crater with diameter of approximately 1 kilometer on Pluto. Then the Hubble's telescope has an aperture of diameter 2.4 meters. Compare the collecting power of the Hubble telescope with the telescope on the spacecraft in 1.2. Then astrophysicists had to decide whether to use a reflecting telescope or a refracting telescope on the spacecraft in 1.2. Which type of telescope would be used? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you have your diagram of your Cassegrain telescope with both mirrors correct and the 2 rays correct. So it looks something like that. Your rays are parallel, they hit the primary mirror, they reflect, they hit the secondary mirror. The lines cross just before they hit the gap in the primary mirror, they then hit the lens and refract through the lens. We know that resolution is going to be the wavelength over the diameter, keep them both in meters, so you get 2.14 times 10 to the minus 6 radians. The smallest detail is therefore going to be equal to the resolution times by the distance it's away from us. So you get 27 meters, which is suitable because that's about 1/40th of the crater's total size. Now in this next one, collecting power is proportional to area, so it's a ratio of the diameters squared, so it's 2.4 squared over 21 squared, which is 130, so it's 130 times bigger. Now the problems of refractors are that they can suffer spherical aberration and chromatic aberration. Reflectors are lighter and reflectors are shorter, so therefore the mirror wouldn't suffer from chromatic aberration. But an issue with reflectors is that the secondary mirror could reduce the brightness, block out some of the light, and cause diffraction effects as well. So you've got to pick which one based on the comparison, but it really should be the reflector. The next question says, draw the ray diagram for a Cassegrain telescope. You should draw paths of two rays initially parallel to the principal axis as far as the eyepiece. A telescope design very similar to the Cassegrain was first proposed by James Gregory in 1663. His telescope design was also the first to include a parabolic primary reflector. The use of a parabolic reflector overcomes the problem of spherical aberration. Draw a diagram to show how spherical aberration is caused by a spherical mirror. Then the first telescope constructed to this design had a primary mirror of diameter 0.15 meters. Calculate the minimum angular separation which could be resolved by this telescope when observing point sources of light of wavelength 630 nanometers and state an appropriate unit. Then the astronomer Edmund Halley claimed to have used his telescope to observe the Cassini division, a dark band in the rings of Saturn. Calculate the angle subtended by the width of this band at the Earth and comment on whether Halley's claim is likely to be valid. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, as we said before, you would draw the following diagram to show the Cassegrain arrangement and the following diagram to show the spherical aberration. Remember, all the lines are parallel to the primary mirror, and then when they reflect off the primary mirror at slightly different angles, therefore they'll cross over at different points, they'll have different foci. If you are further from the axis, their foci occur closer to the mirror. In this next question, we use the Rayleigh criterion. Theta equals lambda over d, same unit, so taking nanometers out into meters, so you get 4.2 times 10 to the minus 6 radians, because that's what we get our values out in the Rayleigh criterion. And this last one, S is equal to r theta, so you can work out theta, which is 3.43 times 10 to the minus 6 radians. Leave your conclusion that it's unlikely to be valid because this angle is smaller than the minimum angular separation we calculated previously, so it's unlikely to have been true. The next question says, draw a ray diagram to show the path of two rays travelling parallel to the principal axis through the Cassegrain telescope. With the aid of the ray diagram, explain what is meant by spherical aberration when applied to a concave mirror, and with the aid of a ray diagram, explain what is meant by chromatic aberration. So pause the video now, then unpause the video when you want to go through your answer. Right, as we said before, with your diagram, the rays reflect the concave or primary mirror, they reflect the convex mirror, and they just cross before the front of the eyepiece lens. The next one, we have different focal points at different distances from the axis, with the shortest focal length for those periaxial rays, like we said before. And then for chromatic aberration, lights at different wavelengths refracted to different foci, with this shown refraction for blue much closer to the lens than that of red. The next question says, the observations of Ceres has been made by the Infrared Telescope Facility in Hawaii. The IRTF consists of a Cassegrain telescope with an objective diameter of 3 meters. Draw a ray diagram for a Cassegrain telescope. The IRTF includes a camera capable of detecting infrared radiation with wavelengths 1 micrometer to 5 micrometers, calculating radians, the smallest angle the telescope could resolve. And then Table 1 summarizes some properties of Ceres, the largest object in the asteroid belt between Mars and Jupiter. Discuss the level of detail IRTF will be able to detect on the surface of Ceres when Ceres is at its closest possible distance to the Earth. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, like we said before, this is the ray diagram for a Cassegrain or a reflecting telescope. Remember, the rays must cross after the secondary mirror. Okay, the next question, use the Rayleigh criterion. It's lambda over d, same units. Now again, the smallest wavelength will give us the smallest angle we can resolve from the equation, so we then say it's 3 meters. In this next one, because you've got the distance there, you can work out that the minimum angular resolution is going to be better or smaller than the size of the asteroid, so you'll get details of about 1/10 the angular size of Ceres, which can be resolved by the telescope. The next question says, the concave mirrors used in some reflecting telescopes can suffer from spherical aberration. Draw a diagram to show what is meant by spherical aberration when it is produced by a concave mirror. Then the International Ultraviolet Explorer, the IUE, and the Grand Telescopal Canaries GTC are two examples of a reflecting telescope. The table below summarises some of the properties of the two telescopes. Compare the two telescopes in terms of location, collecting power and minimum angular resolution. Include calculations to support your comparisons. And the charge coupled device, the CCD, is an important part of the detection system of many modern telescopes due to its high quantum efficiency. Explain what is meant by the term quantum efficiency and compare the quantum efficiency of a CCD with that of the eye. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, again, what's the diagram to show spherical aberration? You've got a concave mirror with parallel incident lines, and they reflect at different focal points because they're hitting the mirror at different angles. Now the rays further from the para-axial line, the one in the middle, will be brought focus nearer to the mirror. So you'll see that they'll be crossing over at different points. Now in our next one, how can we work it through? So first let's think about the location. Well, light has to travel through some of the atmosphere to reach the GTC because it's on the ground. So that affects the amount of light arriving and the resolution. Now because the IUE is in orbit, it'll need its own power source and will need to send information to the ground for analysis. And its position is quite inconvenient and expensive if there needs to be repairs made or to service the actual telescope. Now in terms of collecting power, remember that collecting power is proportional to d squared, so we can say that the ratio is the 10.4 squared over 0.54 squared, so it's 530. So then we'll say the GTC has 530 times the collecting power, so it's going to be better because it'll give you a brighter image. Now the minimum angular resolution links to the Rayleigh criterion of theta equals lambda over d, so you do is proportional to 1 over d. So when you work that through, you get a value of 0.2. So that tells us that the GTC is 5 times better at resolving than the IUE, and so therefore it's going to be better because it'll give a clearer image. Now in this final question, remember what the definition is for a quantum efficiency. It's the number of photons actually detected by the detector divided by the total number of photons incident. Now I know that for CCDs that the quantum efficiency is 80% or above. It's increasing with the advent of modern technology, but the eye is about 1%, so therefore that the CCD is a much more quantumly efficient device. So that brings an end to our revision session today. Hopefully if you've been successful, you can answer A-level physics examination style questions on telescopes. You can assess your understanding of A-level physics on telescopes and then understand what topics you need to improve upon for A-level physics. So thank you so much for listening to this revision session for AQA A-Level Physics Paper 3 on the topic of telescopes for the astrophysics option. Thank you so much and have a lovely day.